Hello and welcome. This is the first video in chapter 26, and in this video there's a couple of important topics. First one is connecting the concept of electric potential from the previous chapter with the concept of the electric field. That's the name of the chapter. And the second important topic in this chapter is the concept of capacitance. And so we're going to go through those in detail in these chapters. The first one I want us to start through is this little diagram here. Now, in this diagram, we've got several different connections between these concepts that we've introduced. The top two, F and U, those are connections that we made in Physics 1, relating the force that a massive particle feels to its potential energy that may be increasing or decreasing. And so the relation between F and U is an integral, right? To go from force on an object to its potential energy, you integrate the force, and to go from potential energy to force, you differentiate. So that one-way or that two-way arrow at the top there is related to kind of the integral derivative relationship, basically the fundamental theorem of calculus. Okay, and on the left-hand side, we got the relationship between force and field. So an electric field from a source charge acts and exerts an electric force equal to Q times E. And we also have the definition of potential in terms of electric potential energy. An object or an electric charge's electric potential energy is equal to its test charge times the magnitude of the potential from the source. So the two bottom ones, the field and the potential, are created by the source charge. The two top ones, force and energy, are the effects of the source charge on test charge, exerting a force and giving a potential energy. And so we'll continue with this definition to investigate the relationship between between field and potential. So the first one is to find the electric potential of a charge distribution if we know its electric field. And if we know its electric field, it's a simple integral. We define the potential. We define the potential at a certain location of a source charge to be the integral of, or the potential difference or voltage between 2 points to be the negative integral between of electric field between those two initial and final locations. So a couple of comments that we can make on this. First of all, that integral, since the electric field is conservative, that integral does not depend on how you go from initial to final. Okay? Any path, okay, any curve from the initial to final location will give you the same answer. This is analogous to gravity. Secondly, there's that negative sign there. That negative sign is there because the electric field always points in the direction of decreasing potential. That's why that negative sign is there. So this is a perfect example of how you can find the potential as a function of location given an electric field. This is an example in the textbook, but it's a lot we can, it's a lot we can talk about actually. The electric field is given. Okay? The electric field is the thing that is constant, and so it's defined on some coordinate system between 0 and 2 meters. And it increases linearly from 0 to 1,000. So the functional form of the electric field, that is the x component of it, is 1,000x. Right? It goes from 0 to 1,000 linearly. So how do we find the potential? Well, we have to just do a simple integral, right? But you have to be careful because in this instance, there's a few things that this example kind of overlooks. And they say, we'll find the potential as a function of location when we set the value of the potential equal to 0 at x equals 0. When we do that, then we go back to the definition. And so we get that the potential is just minus the integral of 1,000x from 0 to the position of interest. And so we get, when we integrate that, we get integral of 1,000x is 500x squared. And so the result is minus 500x squared. And that minus 500x squared gives you the correct initial value of the potential. Okay, we decided in the beginning of the problem, we set the reference of the potential to be 0 at x equals 0. But there's nothing that says we had to do that. Okay, we can set the reference. First of all, we can set the reference potential to be anything. It can be any number, any real number, from negative to positive infinity. The value of the reference potential can be anything. Furthermore, the location of the reference potential can be anything between 0 and 2 meters. Anywhere the electric field is defined, you can set an arbitrary reference value of the potential to be any position where the electric field is defined. So, we could have chosen, for instance, the reference potential to be 0 volts at 1 meter. And what we would have gotten here is we would have gotten a graph that shifted up so that the 0 of the graph is at 1 meter. We could have chosen the reference potential to be 1,000 volts at 1 meter. That would have made it be shifted up even further. So both the choice of the value of the reference potential and the location of that reference potential will basically affect the where this graph is in terms of being shifted up or shifted down. The physical thing, okay, and this is just like setting the 0 of the potential energy. If you remember doing kind of physics 1 problems where a ball drops, you can set the 0 of the potential energy to be at the ceiling or at the ground. The physical thing is that no matter where you set the reference potential at, and no matter what reference potential you set, the difference in potential, which is the voltage between 2 points, always remains exactly the same. That's the physical thing. Here's another example, and this is one that will probably makes sense, starting with the electric field in the s direction of a point charge. Okay, that's the equation here. The electric field in the s direction, that's given. Okay, but one subtle remark here is that we typically, depending on the shape of the charge distribution, that will affect what we can say about the reference potential. Okay, here we encounter a couple of things that are different from the previous example. First of all, the point charge is at the coordinate s equals 0, right? And this is like, s is like a radial coordinate, so this is defined for all space, magnitude, pointing outward. The only place that we may not define the electric potential is at the origin, is at the location of the charge, okay? It's not allowed to set the reference potential to be at the location of the point charge itself. And that's going to also be true if you're dealing with one-dimensional charges. You cannot set the reference potential at the location of the point charge or the line charge. If it's a 2 or 3-dimensional charge, it's fine. You can set it on there. But for reasons, kind of advanced mathematical reasons, you just can't do that on a point or line charge. The other thing is that since the charge is localized, what we mean by localized is that the charge doesn't extend off to infinity, like an infinite line charge or an infinite sheet of charge. If the charge is localized, it's possible for us to set the reference potential at infinity. And so we can set the reference potential to be at infinity, and we can also set that value to be any number that we want. Okay, so in this choice, the convention is that we set the reference potential to be 0 at a location of s equals infinity. That's the specific choice for this. That's the specific choice for this picture. And for any, just about any localized charge, whether it's a dot or like a line segment or one of the spheres of charge, we almost always define the reference potential to have this same convention, to be 0 at infinity. If we're dealing with a plane of charge, sometimes we set the reference potential on the plane. If we're dealing with a line of charge, if it's an infinite line of charge, then the only thing we can do, we can't set it on the line charge. And since it's not localized, we can't set it at infinity either. So the only thing you can do for a line charge is just set the potential at some non-zero, non-infinite location. That's kind of a summary of where and when we can set the reference potentials for different charge distributions. But in this instance, to do the integral, obviously we take we're basically integrating from minus infinity to the location where we want the potential. And so we're going to get a few minus signs, which obviously that minus sign makes it an integral from r to infinity instead of minus integral from infinity to r. So that gets rid of the minus signs, and so we're left with the expected value, and we integrate minus 1 over s squared to get 1 over 4 pi epsilon naught q over r. That's exactly what we expected. Okay. Now let's turn the problem around, right? What did we do here? What did we do in the previous example? We took the integral of the electric field, and we took the antiderivative of essentially minus 1 over s squared, and we got 1 over r, right? The antiderivative of 1 over r squared is minus 1 over r. And with the negative sign, that gives us the correct expression. We could have started, if we knew the potential, we could have gotten the electric field. But there's a subtlety here because the electric field is a vector, which means it can be in 2 dimensions or even 3 dimensions, while the potential is a scalar. So some mechanical analogies, if you think of pressure, right? If you think of pressure, like atmospheric pressure for weather forecasting across the country, right? There's areas of high pressure and there's areas of low pressure, right? That's like the potential. Absolute atmospheric pressure is like the potential of a charge distribution. The electric field would be like the direction of the wind speed, right? The wind speed, it's always going to go, just like these arrows here, the wind speed is always going to go from higher to lower pressure, just like the electric field lines always point from higher to lower potential. Furthermore, they also point along the equipotential surfaces perpendicularly. And well, in this case, we have the value of the electric field is defined as the derivative of the potential minus, of course, because it points against the change in potential. So this bottom right-hand equation, ES being minus dVds, that is for a one-dimensional case where the electric field has symmetry in that direction. But in general, it's going to be a derivative with more than one component. And so you have to do what's called partial derivative. We're not going to be doing that in this class, though. Okay, so this quick example, it's the opposite of what we just did, right? If we know that the electric field is minus the derivative of the potential, then we get our expected value for the point charge. But you could do this with any charge distribution for which you found the potential. And it's worth a few minutes to study the geometry of the electric field in terms of the potential. Okay, a few things to look at here. First of all, we see that the electric field, okay, so the dashed lines are the equipotential surfaces. Those are the lines on which the value of the potential created by the source charge is constant. And so first of all, right, we see that the electric field, it's perpendicular to those surfaces, just like wind speed is perpendicular to the isobars on the weather graphs. That's the first thing. What else do we observe? We also observe that, and there's a partial derivative relationship, we also observe that the size, 0.3, is that electric fields are stronger when the equipotential lines are closer together. So compare the relative sizes of the field vectors on the one on the far left with the one on the right. And the other, that's probably the most important takeaway from this picture, but yeah, that's 3, and then 4. We know that the equipotentials have equal potential value. That's how they're defined. And so that brings to mind what's called the Kirchhoff's loop rule. This is going to be much more practical in the circuits chapters, but we can mention it now by saying that when you start off at a certain location, if you make a closed loop from one end to the next, electric field lines are going to be pointing either perpendicular or tangent to your loop, or some combination. If you make an entire loop, the resulting integral is 0, which means the potential difference between one point as you go an entire loop is 0. And that will be more clear when we introduce electric circuits. Barely even worth introducing at this point. Okay, but this is, but this is kind of the last picture that I want us to see relating potential and field. And this is for conductors. So there's several different features about this graph that I want you to notice. The first being that in a conductor, okay, this is from a review from chapter 22, in a conductor, any excess charge is always on the surface. Okay, but you see here that the surface is not constant curvature. Okay, the surface of a conductor is equipotential. That means the value of the potential is the same everywhere on that surface. It's an equipotential surface, and furthermore, it's actually the same potential as everything inside the interior of the conductor, because the field inside the conductor is 0. Right, that's what point 3 says. Since the electric field inside the conductor is 0, that actually means the potential inside the conductor is the same as the potential on the surface. But here is an interesting point. Okay. Since the equipotential surface is the surface of the conductor, that means the electric field has to point everywhere perpendicular to that conductor. But the final thing that you notice, point 6, and this is something that's kind of new. What you notice is that in this triangular shaped conductor, you have 3 flat surfaces. You have 2, on the left-hand side, you have 2 moderately curved corners, and then you have, on the right-hand side, you have a very sharp curve, sharp point. And it turns out that although the value of electric potential is the same everywhere on this graph, the surface charge density is not, and therefore the electric field is not. Okay, this is kind of strange because the electric field seems to be, you might expect that the field is constant if the potential is constant. That's not true. So it turns out that in a more geometric sense, that the curvature of the surface of the conductor, that's what affects the charge density. And the charge density obviously is what affects the electric field. Okay, so at this sharp point on the right-hand side, you see that there's the most charge piled up on that sharp point. The moderately blunt corners on the left-hand side, you have less charge at those corners, and on the flat surfaces, it's very spread out. So that means that the electric field is going to be largest at the sharp point on the right, still perpendicular. The electric field is going to be smaller at the corners, and it's going to be the minimum on the flat surfaces, because the flat surfaces have the smallest curvature. All right, think about a dresser, right? Or a flat table, a flat rectangular table. You've got 3 points of curvature. You have the flat surface, which has very, very small curvature. you have the long edges, which have a pretty big curvature, and you also have the corners. Well, the corners have the sharpest curvature. And so if you took this table, this rectangular table, and you put some charge on it, then majority of the charge would go to the corners. And the remaining charge would kind of pile up on the edges, the long edges of the table, and only very little of the excess charge would be on the flat surface of the table. That's because the surface charge density on a conductor depends on the curvature. And that's not something that we go into in this class, but you can take like a multivariable calculus class to learn about the, how curvature, how you find the curvature of a surface. That's an advanced topic in math, multivariable calculus. It's a doable topic, but an advanced one nonetheless. So this concludes our intro discussion of chapter 26 and how you relate potential and field. In the next example, we're going to continue with how you can create a potential difference between 2-point charges or between two conductors and lead that to the important concept of capacitance. So until then, thanks for your time, and we'll see you back here for the next video. Take care.